Hello everyone, today we will talk about equilibrium and elasticity. We will solve a few problems on this subject. This is problem set number 1 from tutorial number 2 of the course that I'm teaching. You can find more information at rown.org. I will also provide the PDF files of the problems and the solutions. So let's get to the first problem. The first problem, you have a bunch of books on the table. You want to know how far you can balance the last book on this table, how far from this edge of the table you can balance this last one. If you have n of them, can you go as far as you want, or you gotta stop somewhere? And specifically it's asking, can you make the balance the last one in a way that no part of that book is above the table. Okay, let's get to the solution. Let me zoom in here. Okay. Alright, this is the case only for one book. It's really easy. Let's call this XCM1. Easily you can see that the XCM1, if you use this formula, which is not needed for XCM1 because it's so obvious, and we call this length L, it's going to be L over 2. So this is for one book. Let's get to the more elaborate ones, the two books. So easily graphically you can just connect the center of masses with the line, and then because the masses are the same, let's call the masses M, it's gonna be the center of mass will be the center of this point, of this line that you connect. So you have an M here, you have an M here, and you connect the line, the center will be the center of mass, the CM. And the XCM2, if you look at this, it's at the 3/4 of L. But we want to do the formulas too, so XCM2, using this formula here, it will be 1 over the total mass 2m, the first mass m times this length, this is x, it's L over 2, plus the second one at the length L, this is L, will be 3/4. It's the same solution that we got graphically. Alright, I'm naming this the mass M and this length L, but you can name them 1 and just do the calculation by numbers, but this is more in line with our notation here. That's why I'm doing it. Alright, let's get to the 3 books case. We have 3 books. Let me just put a point at the centers. Again, graphically you can solve this problem by finding the center of mass of these two and put a 2m here. There's a 2m at this point, and there's an m at this point. You draw a line, you go 1/3, and you find the CM, the center of mass, at the end, which should be above this fulcrum point of the table, the edge of the table. This is a graphical way, which you will find that it's 11 over 12. This is, but we want to do it, let me erase these. We want to do it by using the formula, so I will write XCM3 equals 1 over 3m total mass. The first one m times L over 2, second one m times L, the third one m, same mass, times 5 over 4 L. How did I find this 5 over 4? This is half and this is 3/4 we found here. Okay, which will be 11 over 12. 11/12 of L. Okay. This is XCM3. Let me write it here too. Alright, now let me tell you that this is L over 2, this distance from here to here, and the distance is L over 4. This distance from here to here, it's L over 6. So you can see that the XCM3 is L over 2 plus L over 4 plus L over 6. So for n you can now generalize. If you put the first one, it will be of course L over 8, and for n of them we will have L over 2, I'm factoring the first one. 1 plus half plus 1/3 plus dot 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 1/8, 1/4 and dot dot dot, and 1 over n, which is, this is called harmonic series. I'm going to show it with hn. Okay, so this is the claim. Okay, we just guessed that this is going to be the case for n. All right, to be able to prove it, we assume it for n and we show it for n plus 1. That's how you prove this guess. So let's say that this is 2. All right, this is 2 for 2 is tr 2 for n. I'm new with this tablet. Okay. Show that it's 2 for n plus 1. It is 2 for n plus 1, and it's really simple because you know it's true for n. You know that this is this center of mass of the these n here. The next one, the mass is m. This one, the mass is n times m. So you say the xcm of n plus 1 equals 1 over total mass, which is n plus 1 times n m. Okay, and times, okay, the first one is we have n of these masses and they're sitting at this L over 2 h n, okay, plus the one that we're adding here, the one that we will add here. Where does it sit? Okay, let me just draw one here. Okay, this last one should sit on the, okay, of course I drew it wrong. The last one should sit at this point that table meets, because we want these to be in at equilibrium. So this one should be aligned with the table in the previous step, and the table will be here. Okay, the xcm that we're finding, it's here. So you can find that it's xcm n plus the L over 2 plus this L over 2 will give you the position of the last, this last mass. Actually, it's the first mass, the mass that's touching the table. So it's going to be, the mass is m, this mass is n m, this mass is m, it's only one, and the position is this position, L over 2 hn plus L over 2 plus this much. So if you solve this, okay, it's just an exercise, try to simplify this, and you will see that you will get L over 2 times 1 plus times, okay, let me just write it down, times h of n plus 1. So you will get 1 plus half plus third all the way to 1 over n plus 1. Basically, what it does, it says is that this one is adding this term here. So this is how you prove. So now from here you can you actually proved that this is true. So we proved that this formula is true, which is xcm n is L over 2, sorry, this is hn. Okay. Alright, the last comment I'm going to make about this problem is that we asked if any one of these books will pass the table all the way. So I'm going to just leave this as an exercise. Let's put an exercise here. Exercise 2, tutorial number 2, exercise number 1. Or let's code it with ABC. Exercise A, 2A, is find xcm4 for 4 books. Find or basically show that it's 24 or 25L, but let me just say find it and show show that the last book, which is the top one, is after the table, after the edge of the table. Edge of the table. My handwriting is not that good, I know. Okay. Okay. So I think, yeah, that's it for the problem number 1. I'm just gonna roll it from top to bottom once more so you can pause. This is the first page, second, third, and this is the exercise. I'm gonna pause here for a while. All right, and now we can get to the problem number 2. In the problem number 2, there is a ladder leaning on a vertical wall, and there's no friction from between the vertical wall and this ladder, but there's friction between the ground and the ladder, which is a good news. This angle is theta between the vertical wall and the ladder. The mass is m, the length is l, and we want to find the minimum static friction that we should have at this point so that the ladder wouldn't slide. So first thing we gotta, let me zoom in again. Okay, the first thing we should talk about the forces. What are the forces acting on this ladder here? How this ladder interacts with the universe around it, basically. Okay, the first thing is the earth. That's it. This is the force mg. Obviously, the other forces, there is a normal force from here. I'm gonna call it n twiddle because I want to call this one here n. Okay, this is not a straight line, but it's okay. N. So what is the friction force direction? Okay, we don't know what. Well, you can guess that it's in this direction. Oh. Okay. Let's try it here. Fs. This is a static friction, which because we assume that this ladder is hopefully at equilibrium and not moving. Okay. So we found out about the forces, and the point here is that do not draw these forces from one point. When it says free body diagram, you don't do like this: n twiddle, mg, and n and fs. The reason for it, because this is a rigid body, and we will write the torque equation too, the equilibrium for the rotational equilibrium, that the tau should be 0 with respect to any point. So we wouldn't draw it this way. Alright, now I'm gonna make some space here in the middle. Let's move this figure as far as possible. Okay, good. So we found the forces. Equilibrium conditions. What are the equilibrium conditions? That is sigma f equals, instead of ma, because the mass is, the acceleration is 0, so sigma f is 0. If I all the forces I'm adding, and also sigma I, the torque with respect to any point P is 0. This is any point. Alright, the first one, to be able to write down the first one, it's going to give us 2 equations, because this is a 2-dimensional problem, right? There's a vertical direction, y, let's call it, and there is a horizontal direction, x. So for x, we can write there is only this force here, Fs, and this n twiddle here. This is direction x, so let's call it x hat, y hat. Alright, this is gonna be Fs equals n twiddle. And for the vertical direction, we only have n and mg, so they should be equal. Basically, n minus mg equals 0, and I'm just simplifying it. So if you want to write the equation for the torque, well, you can choose any point here. You can choose even this point here. I mean, this can be P. But the problem is you have to do a lot of like calculations and stuff, which is not good news. So let's put the point P at this point down here, so we don't need to calculate for N and Fs, because the lever arm for these two forces will be 0. They're just sitting at that point. So I'm gonna call this point P that we're talking about here. So this one will give us, so this is coming from here, this is coming here, will give us mg. This angle is theta, of course, but this angle is the pi over 2 minus theta. So it's going to be mg sine theta, mg, the length is L, so L over 2. This is L over 2 from here, the center, because it's a uniform ladder. It's a uniform ladder to center of mass is sitting at the center. This is L over 2 sine theta plus, okay, this one is mg is rotating it in the clockwise direction, so let's call this one actually negative. The counterclockwise direction coming from n to idle is positive. Okay, so n to idle times this length L, n to idle times L, times the sine of this angle pi over 2 minus theta, which is cosine theta, is 0. So from here you get n to idle is half mg times tangent theta, half mg times tangent of theta. And you know that this n to idle equals to fs. So if you wanna, because we want to find fs at the end of the day in terms of this mg, which is n. So fs, we found that it's equal to mg over 2 tangent theta. Now we know that the fs is smaller or equal to mu sn. Alright, or you can write this as mu sn, mu s is should be greater or equal to fs over n, which if you put fs from here and n, which is mg, from here you'll find that this is just half tangent of theta. So the minimum of the mu s should be greater or equal to this. The minimum of mu s is when you actually assume that this is just about to slide. So this force is just the right amount to make everything 0 here on these formulas. If it's a little bit smaller than this value here, it doesn't work and it will slide. So the minimum is half tangent theta, and that's it. So this was problem number 2, which actually fits here on this page. Alright everyone, hope you're not sleeping. Okay, let's get moving. Problem number 3. In this problem we want to find the minimum of this force, horizontal force F, so to take this wheel up this bump H. The mass of the wheel is m given and the radius is r. Alright, let's get to the solution. First thing first, we're going to talk about forces, how this wheel interacts with the universe around it. The first thing is Earth, of course, the gravity, mg. The second is the surface, which we have a normal force, and because this is not that normal, I have problem with drawing. Okay, so this is n to idle. Okay, this is coming from the surface, and because there's nothing told in the problem about the friction, we will assume that the friction is 0. So there is only normal force from the surface. Okay, the last forces are coming from this point A, the singular point A. Because it's singular point, we don't know how it acts, so we just assign to it a normal force, which is actually this N. I'm going to call it N. And also, let's say there is a force F, friction force. It's kind of friction. What I did in the class was I kind of assumed that there's no friction here, so the F is 0, and I proved that this N, if the F is 0, this N, which is called the normal force and it's normal to this surface, should be aligned, should be in the line passing through the center of the wheel. So what I did in the class was this, that let me raise this edge. So because there is a force that this edge, the singular edge, is acting on the wheel, there is an opposite force, N, which acts on the ground. Alright, N acts on the ground. And if you think about this ground as an object, then ground, alright. If you think of this N as this ground as an object, and this is the surface that the ground is sitting on, so the normal force, this is normal force. Normal, what does normal mean? Normal to this surface here. And the normal to this surface here is the line passing through the center, because this is a circle. The normal to the circle at any point is the line passing through the center of that circle. So we know that this N is aligned with the center. We know that negative of that vector, which is the vector ground, which is the force ground acting to the wheel, is also aligned with the center of the circle. So the F should be 0. So the force is coming from this point. So, sorry, we already assumed that the F is 0. So the N is aligned with the center of the circle. And we already assumed that the F is 0 in the class, because there's no friction. Alright, but what I'm going to do in this, just to practice with the formulas and writing torque equations and stuff, I'm going to just leave the F there. And we will see that writing the torque equation, we can write a easy torque equation to be able to prove that the F is 0 simply, really simply. This proof is actually came from one of my students, Muhammad Asawir, if I'm pronouncing it correctly. So let's get to the solution. We found out about the forces. We assume that this force is not necessarily, we don't assume that this force is necessarily 0. So let's write the sigma F is 0. Alright, sigma Fi and sigma tau I is 0. So okay, there's only one tau. It can be negative or positive. It's in the, let's see, this is x, y in the z direction. So let's just call it tau at the point P, and adding all the i's equals 0. Okay. We don't need to put the i's. They're just ugly. Okay, good. Now this one is going to give us two equations. One is in the, of course, x direction and y direction. Okay, let's not bore you with these. You already know the F is in this direction positive, and is negative direction. It's going to be negative n. So call this angle theta. It's going to make life easier. Later we will find this theta in terms of this h and r. Okay, we can find this theta in terms of h and r. But for now, let's just call this theta. N times cosine or sine of theta. Let's call it sine of theta. Okay, what else? We have this f here and its positive direction, plus f cosine theta is 0. This is the forces on the x direction. In the y direction we have mg in total and these two. So mg is negative because it's downward. All others are positive. Plus n total plus n cosine theta plus f sine theta is 0. Sigma tau p is 0. Okay, we wrote this equation. Now from here I'm gonna make it really simple, this problem. There's a magical point which is the center of the circle. Right, as one of my students suggested, let's use that point. Tau c is 0. Now you can prove that this f should be 0 really easy, because this mg and f, they don't have any contribution for tau c because they pass through this point. The lever arm is 0. This n twiddle is passing through this point. Again, the lever arm 0. This n is passing through this point. Nothing. This f is the only one remains, and it's acting in this direction, so it's positive. Doesn't matter actually, but anyway, f times r, the radius, is 0, equilibrium condition, which will give us f equals 0. So by this equation we prove that f is 0, and we can just forget about it. So let me just draw a line here and draw 0. Okay, and in these formulas we're gonna say this is 0, so forget about it. There is other condition that will make our life easier, which is the main condition of this problem. It is the condition that we want this wheel to start moving up this bump. To be able to do that, we should think about the moment that this wheel starts to go up. At that moment, this wheel is going to start losing touch with the surface here at the bottom. So the so the condition, let me call this condition. Condition is that n twiddle is 0, because it will start to lose touch here from the surface, and n twiddle will get to 0. So this is our condition, and we will make this condition here. If you put this n twiddle is 0 in these two equations here and solve for f, you'll find that from, let's say this, m1 and 2, from 1 and 2, you can find that f is mg tangent theta. Okay, and the problem is solved. Basically, the only thing you need to know is to find tangent theta in terms of h. This is the h, and this is the r. So you can just draw a circle here and do the calculations. I'm not going to draw the circle. I don't want to make the picture messy and scary. Mg tangent theta will be, okay, it will be kind of dirty. A square root of r squared minus r minus h squared over r minus h. Basically, I'm drawing a triangle here. This is r, and this is r minus h, and this is going to be r squared minus r minus h squared square root. Alright, this is the f we found, and this is the minimum f. Why this is the minimum f? Because we use this condition, n twiddle is 0. If the f is larger than this wheel will start moving. If the f is smaller than this, n twiddle cannot be 0. So this is it for problem number